Hi everyone. I'm going to talk about the central limit theorem today. And let's get started. All right, so the central limit theorem, or what we'll just abbreviate as the CLT, basically applies to a statistical set of some observables. Let us suppose that we have some M group of that measure the same observable in, say, a lab setting. And let us say that these groups are called G1, G2, all the way up to GM. And each of the groups takes some amount of measurements. Let's call them K sub I, where I goes all the way up to M from 1 as well. These can be generally different numbers, but just for simplicity and ease of discussion and later on using M for both just makes it a little easier. All right. Also, the measurements themselves can be different numbers as well from each group. And let's say that each group comes up with an average. We call this X bar sub I. And again, since we have M groups, we should have M averages. And we can take the standard deviation, also having M number of standard deviations from each group. And so what we'll say, or what we can also assume, is that the values of X bar from each group and also their standard deviations will be, in general, different. All right. Also, the histograms in which these groups produce their results and obtain their statistical values of the mean and the standard deviation, those can actually differ from group to group as well, even if all the groups use different bin sizes. All right, this is due to the fact that only a finite number of measurements are taken. What we'll see is that if we were to do, an infinite number of measurements, the distributions should actually come out to be the same in that sense. So ideally, so the ideal Gaussian distribution has not been reached yet in each of the groups. Is still being affected randomly. All right. So how do or how are the values of the mean from each group distributed, and how can they be checked if they are close enough to the actual value itself? To answer this question, let us consider these means from each of the groups as independent variables corresponding to some universal measurement x that we were just describing as being close enough to. That has some particular population mean. And their standard deviations are measured and taken as the random errors for each of those means. All right, so if we take and define these independent variables, just kind of thinking them as a new type of independent variable y, as opposed to the measurements that we described before. There should be m of them from m groups, and their standard deviations are the same. And following an arbitrary distribution, then the variable capital X will look like this, where it's basically just taking the average of the averages themselves. This should follow a Gaussian distribution with an average overall, as stated here as capital X bar, taking the average of Y bar. And the variance of this X capital X is given by sigma squared equal to 1 on m squared, summing over all of the individual errors squared. Taking m to be much greater than 1 so that there's no distinction between RMS values and the sigmas themselves. The above equation for x bar and sigma squared, that should be x, will be shown correct in another context, but the actual proof of the Gaussian distribution will be omitted in this sense, such that what we should hopefully see is that this follows a Gaussian distribution, and the mean is centered upon the mean of the Gaussian itself. So I want to just move back a little bit to a little bit of a review, where we need to review a moment. If we remember the moments that we talked about before in terms of finding expectation values and all these sorts of things that sort of define our statistics of distributions, we will first define two independent variables, capital X and Y. These are separate from the other things that we were talking about before. To find the expectation values and moments about the origin, we define it in this way as mu prime sub r, where r is the power of the independent variable having the expectation value taken over. And both of these, this treatment is done either for discrete function or continuous function in the following manner. The mean itself is defined as the first moment about the origin or the expectation value of x, which we just simply call mu. And usually this is of the population distribution itself. Also, we can take moments about the mean, and these can be a little bit more useful, particularly for higher moments that would be looked at in a statistical manner, particularly for the variance that we described below, and that we oftentimes simply state as sigma squared. This is the second moment about the mean. We define the moment about the mean as mu sub r, and the expectation value is taken of the independent variables, subtracting from the mean and the power r over that subtraction between the two. And again, it follows a similar look to the way that we find the expectation value of simply x to the power r for both discrete and continuous functions. However, again, we're substituting in this x for x minus mu. All right, another thing to note is sometimes the variance is oftentimes shorthanded as VAR of the independent variable x. All right, so this will be something of note in this next slide, where we look at the properties of the expectation values and variances, which have very similar looks to them in the end. Here I just used variance towards the bottom as a means of just showing how that's treated a little bit similarly to the way one would look at the expectation value in the top three for a single power of independent variables. So the useful expectation values and variances that we'll essentially need in order to derive that particular variance that we looked at before, if you're not familiar with how that variance is necessarily derived. in that context, probably the most important one of note is the bottom relationship, where we take the variance times the variance of an independent variable that's multiplied by a scalar and added by a constant. We find that the variance of the independent variable is simply multiplied by the scalar value, the scale value, squared. Note again that these are only applicable if x and y are independent. So just to kind of show the proof of the variance that I described above. Also, we would need the variance of two added independent variables as well, which gives us the variance of each independent variable separately. Because we've defined our independent variable x as 1 on m over the sum of all y's, which were our mean values from each group that we were talking about before, we can then look at the variance of x and see that by taking out that scale of 1 on m, we get a square of 1 on m, so 1 on m squared, times the variance of the sum of all y's. And since the variance of basically a sum of independent variables can be treated as a sum of the variances of the individual variables themselves, we can move that VAR inside the summation and just sum completely over all of the variances. And so therefore we get the proof of how we get this variance of x to equal 1 on m squared times the sum of the variances of just each of those independent variables y sub I. All right, so after that digression, we need to understand that it is important to note that the final distribution is Gaussian no matter what the individual distributions are for the independent variables themselves. So it doesn't matter if the distribution comes from a uniform distribution or from a random sort of whatever distribution it could be. It could also come from a Gaussian distribution, no less, and give us, again, a Gaussian in terms of the distribution of means from each of those measurements from each group. All right. Also important to this is that the larger the set size is, the better the approximation becomes in the end. So we can think as y sub I as a measurement in each group now, and that the average is y bar sub I is the average from each of the groups themselves. So this is how we get capital X bar basically being the sum over y bar on m. Now, I've been sort of linking the independent variable that we're now discussing, y sub I, and this is in relation to x bar sub I, as we essentially treated these means from each group as the new independent variables from each group that we're summing over. And so the average y bar sub I would correspond to the many measurements by the same group. So essentially, if we look at this and look at a large number of measurements being taken by each group, we should expect the average of the entire group itself, of the entire groups that are taking the measurement together, they should be essentially equal to the mean of each individual groups themselves. All right. Now, naturally, this does not have to be so, though the average of the average is the same as all numbers being averaged together at once. So as a proof here, if we're saying that each of the individual averages from each group is then averaged itself, this should give us the average of the total grouping as well. So it doesn't matter if we take the average of each groups and then average it together. Again, this would just simply be the same as taking the entire group's list of numbers or measurements that they've taken and simply just taken the average of all of them together. All right. Now, the next thing to note is that if the errors from each individual group is equal to the basically the error or the standard deviation, sorry, of the entire set, then we can then also say that the variance of our new independent variable x, capital X, I should say, is equal to the variance of the entire group divided by m due to the relationship that we proved before. All right, so this implies that the standard deviation of the mean is equal to the standard deviation of the measurements divided by the square root of the sampling size that we call, in this case, which could be very large and is equal to m in our case. All right, so this gives us an error in the repeated measurements of the mean. So this is why we take our standard deviation of our sample set and then divided by the square root of the sample size whenever we do an experiment of many measurements, because effectively what we're assuming is that the measurement we take each time is a sampling of the mean of a distribution at that exact moment, and we essentially keep continually doing that for a new quote unquote distribution, and we do this many times. All right, so this, as I just mentioned before, also applies to a single measurement when our sigma I sub i's are essentially treated as reading errors. So what we can also do as well is if we just take simply a single reading of whatever, say the voltage across a resistor, and then we use our reading error as the standard deviation of the mean, and this still follows how we would define the typical standard deviation, but now this standard deviation of the mean value, again, would have to be modified by the number of measurements that are taken. In that case, it could be K or M or however many that was taken before. Now, to sort of illustrate the central limit theorem, what I've done here is I've basically rolled a 10-sided dice 150 times. And so this should hopefully give us a uniform distribution. And I've sort of highlighted where the uniform distribution should be located with the blue line across the histogram that I've produced here. I've made it such that this distribution is normalized to unity. Basically, the area under the curve is equal to 1. And so what we would hopefully see is that for a fair 10-sided dice, that we should get a 10% chance of getting any number. And we kind of see that for the most part with this particular distribution. If I were to go more, maybe double the number, we'd probably see a better result in terms of the uniformity of the distribution that we have here. Now, again, this is a discrete uniform distribution, so this has a slightly different statistics involved than, I believe, a continuous discrete function, but I might be wrong on that. But off to the right here, I've sort of shown that if we look at the statistics concerning the discrete uniform distribution, we get an average of 5.51 from our numbers, or from my numbers that I rolled to produce this distribution, and it's fairly close to the theoretical value of 5.5. Only a 0.1% difference in the end between the two. As for the standard deviation, in this case, this is the standard deviation about the origin. I believe it's for the origin, basically the spread of the distribution itself, and we get a standard deviation of about 2.89 from the rolls I produced, and that's not too dissimilar from the 2.87 that should theoretically be produced by this particular distribution. And so that gives us a little less than 1% difference in the end. Now, as if I were to, again, double the number of rolls, I'm sure the average and standard deviations will be much, much better in the end. Now, to take this distribution, I then took subsequent numbers that are next to each other. Basically, I took the list and then I added the two numbers next to each other, then the next two numbers, then the next two numbers, and then I averaged those two. Basically, I just added them and divided them by 2, took the average between two subsequent values, and what we should expect to see is sort of a triangular distribution from our results in whether or not we get a result of 1, 2, 3, 4, 5, 6, 7, 8, or 9, or 10. And so that's sort of displayed here in the blue. And we can kind of see it a little bit. It's not perfect. Also, I don't quite have the triangle probably to the right points and all that sort of stuff. I'm just kind of illustrating where the what the typical shape should look like. It's probably not to unity in this particular view, but we can kind of see that there is an increase at about the mean, which is around 5, 5.5, 6, that area, and we should see a die off towards 10 and 0. And so that's what the green is showing. And the purple, again, is just showing the original uniform distribution that I had before. Now, if I were to take, instead of the 2 subsequent rolls and average them, what if I took the 3 subsequent rolls and started adding them? What would the histogram look like in that regards? Well, now we have this blue shape, which is starting to not look as triangular in some sense. It's starting to kind of have a more rounded shape in that sense. Again, starting to peak around the 5.5 area and dying off towards the ends as well. Now, since I did 150, I tried to do this in making sure that the averages are even and that no numbers are left out of the entire section. But effectively what we're seeing again, if we take 5 numbers, average them, then the next 5, then the next 5, then the next 5, we get this sort of distribution as well. Now do note that the number that this average is producing is not going to be a whole number necessarily. It could be 4.6, it could be 8.1, it could be 0.2, if that was the case. Well, actually, that can't be the case because it has to be 1. 1 is the lowest, I think, yeah. But it can be 1.1 or 2.39 or something. But basically, in this histogram, I've sectioned off if it's between 2 and less than 3, then it goes in the 2 bin. If it's 3 and less than 4, then it goes into the 3 bin, and so on and so forth. So this isn't showing the basically the amount of times that you see 3 occur as an average or 4 occur as an average. This is the number of averages that occur between 3 and 4, and 4 and 5, and 5 and 6, and 6 and 7, and so on and so forth, until we've exhausted all of the possibilities. And so this is the sort of histogram that we're producing in this particular sense. So we may see this more often occur, particularly once we start getting beyond an average of 2 numbers. And you can kind of see that with the orange, we're starting to really get that overall Gaussian shape where it rises up and peaks and then falls back down into a symmetrical fashion. However, one thing to note is that it's not quite Gaussian because it's not peaking at the particular right location. It's peaking closer to 6 rather than 5.5, which is the actual average of the numbers themselves. So if we look at, say, taking 10 subsequent numbers and then averaging those, we actually see a more Gaussian distribution in that sense, even though that it looks kind of asymmetric in this sense. You kind of have to realize that our peak should be located between 5 and 6, basically between these two bars here and these two bars here. So it should peak somewhere in here and then die off symmetrically about those 2 points. Okay, so that basically demonstrates what the central limit theorem shows us, and I hope that sort of elucidates some of the discussion surrounding the central limit theorem and sort of why we take the standard deviation and divide it by the square root of the sample size in order to find the error about the mean value when we look at particular sets of data. And I hope that is helpful. So I'll talk to you guys later.